Okay, so some names of representative elements. Again, our representative elements are S blocks and our P block. Okay, those are only our representative elements. Transition elements are not part of that. Now we're going to go through each of these groups and we're going to look at them and we're going to talk about some properties of each of these groups, and then I'll have a demo for you in a few minutes. Okay? So the first group is the alkali metals, group 1. Alkali metals are the most reactive group of metals on the periodic table. These metals are so reactive, we have to keep them under oil because they will react with the air itself. So all these metals must be kept under oil. They're the most reactive metals on the periodic table. Francium down here is the most reactive down here. Okay? They all have one valence electron. So they all have one electron in their outermost shell. That's why they are so reactive. Okay? And they're very soft. I just cut them with a very dull knife. It was sharp at one time, but it's not sharp anymore. But they're very, very soft. So I'll get them out and I will show them to you in a little bit. Okay? Then we have the alkaline earth metals. It's group 2. The alkaline earth metals are not as reactive as group 1. They're reactive in their own right, but they're not terribly reactive. Not very soft either. They have 2 valence electrons, so they're a little more stable than group 1. So they're not as reactive as group 1. Does that make sense? The halogens are group 17. The halogens are over here, way over here next to the noble gases, group 17. We skip all these. These don't have no common names. But group 17 are the halogens. The halogens are the most reactive nonmetals on the periodic table. They're terribly reactive. They will strip electrons off just about anything. They're so reactive, they react with themselves. They do not want to be alone. They're used as antiseptics. Fluorine, or fluoride for your teeth. Chlorine, obviously, we clean up our pools or Clorox or stuff like that. They kill germs. Bromine is the orangey stuff. It's bromines in that substance. If you've ever had surgery, they put the bromine solution around it and they cut through it. And it'll sticky afterwards. That's so if any bacteria and stuff land on that down the road, it helps prevent infection. And iodine was something my parents always used. It's called methylate or tincture of iodine, and they'd put on cuts and sores, and it would burn like the dickens. It was so awful. And it would leave your skin brown, like almost a purpley color. So it was interesting. But halogens are extremely reactive. They have 7 valence electrons. They only want 1 electron to complete their outermost shell, so they take it away from almost anything, including themselves. Actually, they share it with themselves. But they want these electrons. Okay? And because they share it with themselves, there are these things called diatomic molecules. These diatomic molecules will always be found in pairs. The hydrogen, nitrogen, oxygen, and the halogens. And I've taken the liberty of putting green dots on them on the periodic table. If you look up here, the green dots indicate these are diatomic. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Okay? There's 7 of them. And look how it makes the 7. It makes the 7. I think it's kind of interesting. Hydrogen's 1 as well, though, but it's way over there. It's kind of like a little accent marker or something. So there's 7 diatomic molecules. They are always found in pairs when they're by themselves, when it's an element. So H2, N2, O2, F2, I2, Br2, and Cl2. That's how we'll always see them. That make sense? Yep. Okay, good. So I think this is noble gas. I'm sorry, I did forget these. Noble gases are the most non-reactive elements on the periodic table. They are inert. Inert means not reactive. And they're not reactive because they have 8 valence electrons. They don't need any more valence electrons. All atoms want are 8 valence electrons. So if they've got them, why should they react? They don't need to. So these guys, we electrify them to get really pretty colors. We use krypton in our lightning ball or plasma ball over there. Xenon. I actually think they're actually using xenon to somehow make helium artificially. I don't know how. I read that somewhere. I'm not quite sure though. I may be making it up. Who knows? Transition metals. Transition metals are this middle section over here. They're a hodgepodge of all kinds of different elements. The transitions are your D block. You have your coinage elements, metals up here, your copper, your silver, your gold, platinum, nickel. Those are your coinage metals. You have your life metals like your iron, cobalt, zinc, things we need for our life, for minerals. And then we have our structural metals like iron, osmium, technetium, things like that. So you have just all kinds of properties with these transition metals. So we just lump them as a big group. Now down here, the next group is the inner transitions. The F group is called the inner transitions, or rare earth elements. But each of the F4 and F5, they each have their own name. 4F is called the lanthanide series. So 4F is called the lanthanide series. And the lanthanide series are just an extension of the periodic table. There's nothing major, nothing exciting about them. They all kind of look alike actually, don't they? They're just a group of gray metal elements. But the next one is fun. The actinide series now, that's a different story. The actinide series are your radioactive elements. This is what phrenologists used to make right here. This is called a uranium derby. They used to take the ore from different things they brought in, and they melt it down and extract the uranium ore and make it in these little discs. And they'd ship these discs off to places like Oak Ridge, Tennessee, or Savannah River, Georgia, or Los Alamos, New Mexico, and things like that, to be used in nuclear reactors, nuclear bombs, nuclear facilities of some sort. But that's what they're used for. Americesium is actually in your smoke detectors. If you pull off your smoke detector back, you'll see this little radioactive sign right there. With something's radioactive, it's emitting particles. It's emitting alpha, beta, gamma radiation constantly. It never stops. It's just constantly giving off these particles. Well, as it gives off the particles, there's a sensor over here that senses these particles are coming off. Well, smoke gets in there and blocks the sensor from the radioactive material. That's when your smoke detector starts going off, because it's not picking it up anymore. So that's how they work. So if you look at it, they're in there. And this is plutonium, a nice silvery piece of plutonium. But the thing is, with the actinide series, everything after uranium is called a transuranium element. These are transuranium. Means they're all after uranium. And notice how they're all hollowed out. What's a hollowing out mean? They're man-made. Anything that's just a hollowed letter is a man-made element. What's the dark black bold mean? Means it's, I'm sorry? Solid. So black, it means solid. Red means gas. And blue liquid. Means liquid. So when you look up here, you can say, okay, so look what you've learned so far. Now you know these are the most reactive metals, and these are the most reactive nonmetals. Okay? We know these aren't reactive at all. We know that at room temperature, this periodic table is at room temperature. At room temperature, platinum is a solid. At room temperature, mercury is a liquid. At room temperature, bromine's a liquid. Chlorine's a gas. All these things come into play when we start talking about reactions. Okay? Yeah? You good? Okay. So, here are our periodic table of elements. I love this periodic table. I just think it's so pretty. I can hang this on my wall. I have a big periodic table of desserts in my kitchen. They just took all the symbols and put desserts after them instead. It's kind of fun. But it's very pretty. Any questions now about the periodic table, Sean?
Carbon? I thought carbon was a gas.
No, carbon's a solid. No. Carbon is like coal. That's what carbon is as well. So on the test, I will ask you things like to identify the different groups, to know the properties of the groups, to tell me if things are metals or nonmetals, to tell me the properties of metals and nonmetals, to talk about Dmitry Mendeleev and what he contributed, what Moseley contributed, and you know your symbols and names, right? So that's the first part of this chapter. So far, so good. So we know what to do so far? Okay. Yes, sir.
So you know the ones that you made us memorize?
Mm-hmm.
Are those the only ones that we need to know right now? Or?
That's the only ones you need to know like this. Yes. I will. You don't have to memorize the whole periodic table. No. Those are the ones we use most of the time. I mean, very seldom do I ask you about cerium or Einsteinium or Galladium. We don't use those. But the most common ones, the 40 most common, are the ones you had to memorize. Okay? Now we're going to look at periodic trends. You guys know what a trend is? What's a trend? Right now, at one point in time, dapping was a trend. Everyone, or the floss, knows how to put this on tape. You know, floss is a trend, right? A trend is something. Does everyone do trends? So when the whole flossing thing was out and about, did everyone floss in here? No. I mean that's kind of a weak trend, but in the 70s, you think of the 70s, you think of people with big old bell bottoms and big wide belts. You know, that was a trend, how you dressed, with a fringe and tie-dyed shirts. I was living in the 70s. I never dressed like that. You know, so that's what you think of. That was a trend you thought of, right? So periodic trends are things that happen typically on a periodic table. Do they always happen? No. It's a trend. This is what typically happens, okay? And these are all different trends, and you're going to learn about all of them. And you're going to be able to predict things on the periodic table yourself. So first, atomic radius. Atomic radius has to do with size. How big is the atom? Okay? So we measure an atom from the center of its nucleus to its outermost electron. That is an atomic radius. So we go from the center of the nucleus to its outermost electron. Obviously, this atom has a smaller atomic radius than this atom. Right? Now, one trend we've seen is this, that as you go down a column or a group, what happens to the atomic radius?
It gets bigger.
It gets bigger. Why does it get bigger? Why do they get bigger as they go down the column?
Because of mass.
Well, mass gets bigger, yes. That's not the reason.
The electronic radius of the outermost electron is more low.
It's a good thought, but that's not the reason. What happens as you go down? What is the outermost electron configuration for rubidium? What is the valence shell for rubidium? Sorry?
7s1.
Oh, well, the very, very bottom is 7s1. You're right. But, okay, then what about for lithium? What's lithium's outermost shell? 2s1. What's that 2 and that 7 mean? You said 7s1 and 2s1. What's the 7 and the 2 mean? Not electrons. How many shells? Thank you, Kevin. How many shells they have? So every time I go down in the group, I add a shell, and I add a shell, and I add a shell. And you know what happens when you put on a shirt, then another shirt, then another shirt, and what happens? You start getting bigger, don't you? I always think of the little kid on Christmas Story when she puts all his clothes on him and he falls over and he can't get up, right? It's like a shell and a shell. So obviously, just by the fact that you're adding a shell, it's going to get bigger, right? Yay, that's exactly it. They get bigger because they add a shell. But what's this have to do with anything? The larger the element, the more reactive it is. So I can look at the periodic table and say, lithium's going to react, but potassium's going to react really well. Rubidium's going to act even more. Cesium's going to be even a greater reaction, and francium's going to be out of this world. So as I come down this group down here, these guys become more reactive. Francium is the most reactive metal on the periodic table. So francium is the most reactive metal on the periodic table. So far, so good. Now let me show you some of this stuff. Let's see. Real quick, guys, I want to show you this next slide. So the atomic radius increases going down each group of representative elements only. These are our S blocks and P block. Okay? So now we're going to look at the alkali metals. I'm going to take my little robot on a little ride here. Woo! Bring it over here. I'm going to put it, just don't stop moving on me. Yeah, I'll sit over here so you can see. There you go. Okay, hopefully you can see what's going on. Okay, so what I have back here, I have three elements. I have lithium, potassium, and sodium. We're not allowed to keep cesium or rubidium on site. They're too, obviously, francium. Francium actually never exists in nature by itself. It's so reactive, it just reacts as soon as it comes out of its, well, as soon as it exposes itself, it reacts. So I have lithium, potassium, and sodium. And we know that they're extremely reactive with water. So we're going to get some water in here. That sounds like a great idea, doesn't it? I'm going to try to put this. I'm going to put this over here next to you, if you don't mind. I know you're giving a hissy there. Okay. So hopefully it'll be able to see the water. There you go. Okay. So we'll do lithium first. We'll start with the smallest atom. We have to keep these under oil because obviously they are very reactive. So we got to wipe the oil off of them first. Now lithium isn't as soft as the other two. Have to kind of pry it apart a little bit. And it's going to react very quickly. It's going to turn. We call it corroding. It's going to, oh, that was bad. Got that one on tape, didn't I? It'll corrode very quickly because it is kind of moist out right now. But this is lithium. Okay? Lithium is this soft gray metal. Oh, now it's falling around. And see how it's turning black around the edges where I cut it? It's because it is reacting with the water in the air right now. So it's trying to protect itself. It's oxidizing out here. See how and if I cut it again, see if I can get it. It's kind of hard. Oh. There you go. See how shiny it is now on the inside? Okay. Now when I put this in water, it's going to react somewhat violently because it wants to react very quickly. It only has one valence electron, and it's like, I want to get rid of this electron as quickly as I possibly can because I really don't want one electron. If I lose one electron, I'm going to have a complete outermost shell, and that's exactly what I want. I'm sorry. What? It wants a complete outermost shell. So that's what all atoms want.
You want to lose?
I want to lose an electron.
But the other one's want to gain one.
Yes. The nonmetals want to gain electrons, and the metals want to lose them. So, I'm going to take this guy and put up a little bit. Okay, my tweezers back out. This back over here. And we drop it in. You'll see it fizzing. It's producing hydrogen right now. And eventually maybe the people in the front row over here are going to smell it. You're going to choke a little bit. Hydrogen just kind of tickles your... That choke makes you tickles your throat. You just can't... Like, but it doesn't do much but fizz around and generate hydrogen. It's kind of, it's small.
Highly reactive.
It's very reactive, but it's just not volatile enough. Not for us, right? We want more. So let me put a couple more in here just to get rid of them. Lithium's pretty docile for the most part. Can you hear it though? Like a frying egg or something, doesn't it? Let's see if you can smell the hydrogen. Oh, goodness gracious. It just chokes you. It's just really weird. I mean, it doesn't make you feel nauseous, and it just kind of tickles your throat when you got a cough. I'm really sensitive to it for some reason. But anyway, that's lithium. Lithium's It's here. Hold my breath. Okay, back again I go. Whew. Okay, let's get some more water. You smell it? Just tickles a little bit. Now let's look at sodium. Sodium. Oh goodness. Let's see. Here's sodium. Sodium's a lighter color than lithium. It has a real thick coating on it of oxidation. And look how soft it is. It's kind of like wet clay, or cold clay, I should say. See how shiny it is? Yeah. Doesn't look like a metal. It looks like clay.
What is it?
Sodium. Oh. Sodium metal. I'm going to cut it up as I walk around. It's just easier. See how shiny it is on the inside? It won't stay shiny long. Okay. Sorry. Starting to smell the hydrogen. See how shiny it is on the inside. It's shiny, shiny, shiny. I feel gross after this because it's so oily. See how shiny it is.
I don't smell anything.
Yeah, it's kind of a... Sorry. Shiny it is. Shiny, shiny. Yeah, it just kind of catches your breath, doesn't it? I'm sorry. Oh no, I got everyone coughing. So it kind of looks like wet, like clay, and it cuts it like too. If you look, it goes. It kind of cuts. Really soft. Okay. This is sodium. So sodium's a little larger. Now, if I could get someone to turn the light off for me, Leanne, would you do that, please? And, whoop, let me see if I can find it now. We never know what sodium's going to do at first, but so we kind of watch it. Whoop. But it does. Is it more reactive than lithium?
Yeah.
Yes. Whoop. Oh, goodness. Oh, wow. We never kind of know what sodium's going to do. I'm glad we got that on tape. That's wonderful. Well, that was exciting. Is it on? We turn the lights on for a second. Let's make sure. It's fine. It's fine. Let's do a couple more pieces and see what's going on with it. I'm going to move this back a little bit. We'll turn the lights off again and we'll see.
Oh, we're going to do it again?
Oh, of course. You just never know. Sometimes it does that. I've done this all day today, and that was the first time I did that. We're all like holding our breath. Oh, what's it gonna do? It just dances around the fire. Isn't it kind of pretty though? And notice the color of it. Notice the color of this flame. We still have to do potassium. What's the color of the flame you see? Orange. Remember when you put the sodium chloride in the flame? What color was the sodium chloride when you burned it? Orange. So sodium always burns with an orange flame. Always. Okay? So far so good? Yep. Let's see how many. I got one more small piece I'll throw in there. No. I know better on that one. You know, and sometimes it reacts and sometimes it doesn't. Okay, well, there you go. Usually the Pyrex is enough to hold it. If you notice that, reach your light on for me, someone. If you notice, you look up here, it blew the water out first. The water's on the floor and the water's on the table. Typically, it doesn't break the glass. Pyrex is very, very strong glass. But now we've got the next one a little bit bigger. Potassium. Poor Sarah. Sarah's like, oh my gosh, should you put another one in? Whoops. Do this. Sarah's like, That water here. Okay, potassium. Let me dry my hands off. I think that would be a wise move. I don't want to get water on my hands. What happened to Mrs. Cottingham today? I don't know. She was on fire in her lecture. Yeah, get on fire. Now, potassium is crunchy. Yeah, it's kind of. It almost feels like it's coated with salt. No.
You didn't dry off with the wet paper towel.
It's oil. It's an oil paper towel. So if you look at potassium, guys, it's real. It just smushes. It's so soft it just smushes down. Maybe this will let the bunches go. Whoop. Just smush. It's like clay. It's like room temperature clay. It's really, really soft. Show it like that. Really soft. And if you look up here, I'll show you over here. See how this smashes down. I didn't see it or not, but it just smushes like gum. Okay? Sorry, I'm going to take my knife at you. To my hand. There you go.
What would happen if you put like a huge amount of sodium in the lake?
It would blow up. You've probably seen that video before.
No.
Oh yeah, people launch it like catapults. So the only thing is though, but the problem is, I don't know why people do that, because animals that live in the lake are going to be affected because it makes sodium hydroxide, which is like drain cleaner. And that's just so not cool. You just, it would then blow. It would go. Yes. So look how I smushed it down. It just smushes. Smushy, smushy, smushy.
That's your idea.
Smushy, smushy. Okay? Can you hit the lights for me again? Wait, let me cut it up first so I can see what I'm doing. No? I like my job a little too much.
Just move that pile down.
I need to keep an eye on that, make sure.
Oh, yeah. Just catch it.
Whoops.
Put some water on it.
That would be a good idea. Not.
Throw it all. Throw it all on it. You never put water on a chemical fire.
Exactly. Well done. Someone listened to their. Okay, now you can turn off the lights. I said that before I picked. Here's the tweezers. Okay, ready? Whoa.
You gotta wait for that one quick.
Yeah. Sarah's like, I'm getting ready to run. I'm getting ready to run. Now notice the color of this flame.
Purple.
I'll move it
White.
back.
Definitely that's white.
That is white.
That is violet.
That's violet. Yeah, it's like a violet. Oh, Remember what happened? The color you saw when you did potassium chloride? It's a violet color. Woo!
Now, play the rest of that.
No.
What if we put one of each in?
Nothing. Just make different color flags.
We should do it. Just a small piece. Bam.
They'd probably go together and just make one color flame. Yeah. And then a little last little piece. Ooh, it is nice. You turn the lights on for me again. So that is, now watch, the unfortunate part with potassium is it tends to pop and stick on the side. So every time I pour it out, it'll start. Sometimes it like, sparks up again. But, so which is the most reactive of those three elements?
Potassium.
Potassium. Which one's furthest down on the column?
Potassium.
Potassium. So the larger the atom, the more reactive it is. Okay? So when I look at the periodic table, I say, well, I want a really fast reaction with a metal, of what I have. I'm going to use the potassium-based ones. So that'll be a little bit faster, a little bit more volatile reaction. Okay? Does that make sense?
Yes.
Yes, sir.
So oil and water separate. If you have a 50-50 oil and water and you drop one of them, what will it do?
Well, I had that actually happen once, a long time ago when I was at Withrow High School. It didn't actually, I didn't have oil in it, but it was really old sodium. And so I took it out and I put it in, into, I had a smaller beaker. And it sunk. Instead of, how as soon as I hit, it fizzes around. It didn't do that. It sunk to the bottom. And I was like, well, that's really weird. And it made a layer of oil just above it. Like the oil and the water kind of made this like flipped, what's that layer called? Like a thermo layer or something. And so when the hydrogen gas came off, the reason it catches on fire is it's giving off hydrogen gas. It's a really hot reaction. It gives off a lot of heat and it catches the gas on fire. Well, it did that. It gave off all the heat, went to catch on fire, but was trapped under the oil, and then all of the water, burning metal, it was like raining. The kids all screamed. It was mayhem. It didn't break though. The beaker didn't break, but I was like, oh my goodness. My first year as a teacher, and that happens, and I was like, I'll be fired. I wasn't. The kids all thought it was really cool. Do it again. I'm like, and it's never happened again. Because now I wipe off all the oil. Do you notice I kept taking the paper towel? I learned from my mistakes. I would never put an oily piece of metal in there again. It was scary. Okay, I'll take the little robot back up with me. Oh, hello. Okay, any questions so far? Not so far? Okay, and I do believe that is the end of our, notes for now. Okay, yeah, we'll start the rest of the atomic trend. Oops.